This is chapter 8, complex numbers and polar coordinates, and notice that I'm only going to do the first couple of sections, complex numbers, and then trigonometric form for complex numbers, so chapters 8.1 and 8.2. Alright, so I'm just going to read this. Complex numbers, what did pi say to I? Get real. What did I say to pi? Be rational. Alright, behind the joke. Motivation at this particular website. However, in quantum mechanics, complex numbers aren't just a convenience, they're necessary. The fundamental equation in quantum physics, the Schrödinger equation, named for the same dude as the cat, has an imaginary number in it, and the solutions to the equation are inherently complex numbers. These solutions are called wave functions since they are wave-like in character. In Paul Nahin's book, An Imaginary Tale, the story of square root of -1, a few applications are listed, such as, but what really perplexed Cardan was the case of such square roots of negative numbers occurring in the Cardan formula for cubic equations that clearly had only real solutions, polynomials in general. And yet, in the early days of the study of alternating electrical currents, the well-known AC, he ran into a situation that, in his word, was peculiar. With complex exponentials, however, Rayleigh's puzzle is not too hard to resolve, and that is exactly how Rayleigh himself was able to explain matters. So what I am going to do is show you just the very beginnings of modern complex theory, complex integration, as initiated by the French genius Augustin Louis Cauchy. All right. Definition. Z equals a plus bi with I equals the square root of -1 is a complex number. The parts of Z are the real part A and the imaginary part B. It is obvious that I squared equals -1. Right? You can see that square root of -1 squared will be that -1 that you have under the radical, and that is then I squared equals -1. Next definition. Two complex numbers Z1 and Z2 are added or subtracted by combining their real parts A1 and A2 and separately their imaginary parts B1 and B2. Really straightforward. Next definition. Two complex numbers Z1 and Z2 are multiplied using the distributive law and akin to multiplying binomials, which is the FOIL method. The first and the last partial products, A1 times A2 and B1i times B2i equals negative B1, B2. Notice that the I squared in here produces that negative, combined to the real part of the product. And the outer and the inner partial products, A1 times B2i and B1i times A2 combined to the imaginary part of the product. Division of complex numbers uses a detour. So just like it always is, we don't necessarily like to divide by things. Same thing happens with complex numbers. The definition is two complex numbers Z equals A plus BI and Z asterisk equals A minus BI, which are complex conjugates of each other. So notice A plus BI versus A minus BI. So they're complex conjugates of each other are multiplied akin to the difference of squares. So Z times its conjugate, Z asterisk, equals simply A squared plus B squared. So notice in this case it's actually not a difference. Oh, of course this results in the sum of squares because I squared cancels the minus resulting from the multiplication. So usually it's a difference of squares. In this case it's an addition of squares, but that's due to the complex numbers that are involved. The result then is a real number. Okay. Therefore, the division of complex numbers Z1 and Z2 is accomplished by multiplying both the numerator and the denominator with the complex conjugate Z2 asterisk of the denominator. So that is here Z1 over Z2 equals Z1 times Z2 asterisk divided by Z2 times Z2 asterisk. And then, of course, in the denominator, we would get A squared plus B squared. While the numerator remains a complex number, the denominator is now a real number. Thus, the quotient is a complex number itself, and we got rid of the complex number in the denominator. So for chapter 8.1, complex numbers, here are some problems. So the first one here, write each expression in terms of I. So square root of -121. Square root of 121 is easy. that's 11. Square root of negative 1 is I. So here it is, 11i. Square root of negative 400. Square root of 400 is 20. Square root of negative 1 is I, so 20i. Square root of negative 18, and I have to shift this over here. There we go. So square root of negative 18 is square root of negative 1, again, is I. And then square root of 18 is square root of 2 times 9. Square root of 9 is 3. So 3 goes to the front, and 2 stays on the radical. So it's 3 times the square root of 2 times I. Something similar happens with the square root of 45. 45 is 9 times 5. Square root of 9 is 3. The 5 stays on the radical, and of course square root of negative 1 is I. So we're going to get this one here, 3 times the square root of 5 times I. All right, the next problem then. Find all in xy for these equations so that each of these equations is true. So cosine x plus I times sine y equals sine x plus I. All right. Separate real and imaginary parts. So, excuse me, we're going to get cosine x equals sine x. There it is. And then that only works for 45 degrees. That's when the two are equal to each other. So it's going to be at pi over 4, which is in the first quadrant, and it also happens at 225 degrees, which is in the third quadrant, so the other one is 5/4 times pi. And then we're going to look at the y. So that's going to be I times sine y equals I times 1. I put the 1 there in order to show that that actually is simply sine y equals 1, which is 90 degrees. So it's pi over 2. There it is. All right, and this problem, sine squared x plus 1 plus I times tangent y equals 2 sine x minus I, and you can see that I color-coded these. So separate real and imaginary parts. And I'm going to start with the real parts. So on the left, sine squared x plus 1 equals what's on the right, 2 times sine x. All right, so I'm going to get that all to the left-hand side. So sine squared x minus 2 sine x plus 1 equals 0. Now I'm going to factor. This is a nice perfect squared trinomial. There it is. Sine x minus 1 squared equals 0. And we can look at the solution that the only way this works is if the sine x equals 1 itself, in which case that only happens at 90 degrees, and therefore it's going to be pi over 2. There it is. And then plus, yes, plus any subsequent 2 pi on top of that. So at 450 degrees and 710 degrees and so on. So add 2k pi to that. I'm going to scroll down a little bit. Now I'm going to do the imaginary parts. So on the left, I tangent y equals negative I times 1. Now, basically we can say, hey, the I divides out. By the way, we have to be careful with that. We don't necessarily want to divide by I. I suggest simply multiply by I on both sides, and you will see that that I squared on both sides introduces a negative 1 on both sides, which means either way they're gone. So we have actually tangent y equals negative 1. So if it was 1, we would be at 45 degrees, but the negative 1 says that we're going to be in the second quadrant, and there it's going to be the 135 degrees rather than the 45 degrees. So when I post that solution to that, there it is. 135 degrees, which is 3/4 pi. And then it happens again in the fourth quadrant, which is the, I'm sorry. Yes, that's correct. In the fourth quadrant, 7/4 pi, which would be 315 degrees for the tangent y to be equal to -1. All right, so these problems combine the following complex numbers. This is addition and subtraction, and it's really straightforward. This one here, 7 plus 2i plus 3 minus 4i. Well, 7 plus 3 is 10. 2i minus 4i is minus 2i. There it is. 3 minus 5i plus 2 plus 4i. Well, it's going to be 5 minus 1i, which is, of course, 5 minus I. There you go. 5 plus 2i minus 3 plus 6i in parentheses. So it's going to be 2 and then minus 4i. 6 plus 7i, and I have to push that in here. So 6 plus 7i minus 4 plus I. So that's going to be in parentheses. So it's going to be 6 minus 4 is 2, and 7i minus I is 6i. And there we go. All right, next set of problems. So simplify each power of I. I to the first power is simply I. I squared, well, that's I times I, which is by definition -1. Well, I cubed is going to be I squared, which is -1, times another I. So it's going to be -I. And I to the fourth is, well, I squared times I squared, which is going to be -1 times -1, which is +1. There we go. And now it gets interesting. This looks complicated here, the I to the 12th and then the I to the 13th, but they're not. Notice 12 is 3 times the 4, so it's basically I to the 4th, which is 1, which is 1, times another I to the 4, which is 1, times another I to the 4, which is 1. So 1 times 1 times 1 times 1, that's 1. So that means that this repeats every 4 powers of I. So I to the 4th, I to the 8th, I to the 12th, I to the 16th. Notice down here, I to the 30, I to the 32 will all be 1. And then I to the 13, well, that's I to the 12th times another I. So 1 times I, which is I. I keep saying I all over the place here. So I to the 15, well, it's the same as I to the 3rd, because it would be I to the 3rd, I to the 7th, I to the 15. They're all -I. There it is. And it would continue on. I to the 19th, I to the 23rd, and so on. So I to the 14th is the same as this one here. So I squared, which is -1. Again, it's I squared, I to the 6th, I to the 10th, I to the 14th, and so on. Same thing, by the way, for I to the 34. I to the 32nd would be 1 again, and then times another I squared. Well, that's -1. So there it is. I to the 32nd, there it is, 1. I to the 33, we're back to I. And, whoops, okay. Oopsie. There we go, I. And I to the 35th, well, that's I to the 32, which is 1, times I to the 3rd, which is -I. And there it is. All right, find the following products. Yeah, it's going to be a little harder. It's going to be a little bit harder, but not too bad. It's simply the following method. So 2 plus 4i times 3 minus I, both of them in parentheses. So I'm going to get 6 in the front. Here, I'm just going to put it there. There it is. So 6 is the first part, then minus 4i squared. That's actually the last part, so I put it there. So I put already the real parts right next to each other. Then I'm going to have minus 2i, which is the outer part, and then I have plus 2i, 12i, which is the inner part. And then you can see that 6 minus 4i squared, well, that's a -1 there. That gets rid of that minus that's already there. So 6 plus 4, actually, which is 10. And then minus 2i plus 12i is minus 10i. There you go. Sorry, plus 10i. There it is. And I think you could see that, right? So this one here is going to be, there's a 9 in the front, then there's going to be a plus 4i squared, then that would be the first and the last part, and then there's going to be minus 6i and another minus 6i. And there they are. and then that plus 4i squared that you see kind of like in second place, well, it turns into a minus 4, so 9 minus 4 is 5, and then minus 12i, and there it is. All right, so 4 plus 5i in parentheses times 4 minus 5i in parentheses. Well, that's a complex conjugate there, so that's going to give us the nice difference of squares. Respectively, for complex numbers, it's going to be the nice sum of squares. So it's basically going to be 16 plus 25, 41. That's it. But here's the intermediate step. Here it is. So there's the 16 in the front. Then you have the 20 minus 25i squared, so the first and the last part. And of course, the I squared is negative 1, which gets rid of that minus right here. So it's going to be plus 25, 16 plus 25 is the 41. And then the inner and the outer part, they are actually gone. They add up to 0, which is the idea behind the difference of squares. And in this case, the complex conjugate here, which is the sum of squares. And so as they're gone, it's simply, the sum of squares. And there it is. 41. All right, so these problems here, to see how I position these. All right, now it gets more interesting, right? So find the following here. 3 plus 2i divide by 3 minus 2i. So we need to get rid of that complex denominator. And we do that by multiplying with the complex conjugate in both the numerator and the denominator. So times 3 plus 2i in both numerator and denominator. So there it is. All right. In the denominator, that becomes really nice. We're going to have 3 times 3 is 9. 2 times 2 is 4. And actually, it's going to be a minus 4i squared, which will turn into a plus soon. And then, of course, the numerator looks more complicated with, again, the FOIL here. 9 plus 4i squared plus 6i plus another 6i, because it's a perfect square trinomial. And notice that I already arranged the real parts and imaginary parts. In the denominator, it's 9 minus 4i squared, which soon will turn into 13. 9 plus 4, right? And there it is. And then the numerator sums up to a 5 for the real part. So 9 minus 4 actually then, and then plus the 12i. And that's actually it. The only other thing to do here is to separate the real from the imaginary part. So 5 over 13 plus 12 over 13i. All right, the next one, 2 plus I divided by 5 minus 6i. Again with the complex conjugate, which means multiply numerator and denominator with 5 plus 6i. By the way, I'm not sure if the other one was actually on the screen. There we go. The previous problem. So multiply both numerator and the denominator with 5 plus 6i. And there it is. That means now in the denominator, we're going to have 25 minus 36i squared. And there it is. And you can see that in the numerator, we have the typical FOIL going on here. So 10 plus 6i squared plus 12i plus 5i, which is going to give us 10 minus 6 actually, which is 4, and then plus 17i, and in the denominator we're going to have 25 plus 36 actually, which is 61, and there it is. And then we separate the real from the imaginary part, so 4 over 61 plus 17 over 61i. There is nothing to simplify here. We cannot add the imaginary part to the real part. Complex numbers always have two parts, one of them imaginary, the other one real. They cannot be added or subtracted together. All right.